The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so remember we've seen Stokes' theorem, which says if I have a closed curve in space bounding some surface S, and I orient the curve and the surface compatibly with each other, then I can compute a line integral along C, along my curve, in terms of, instead, a surface integral for flux of a different vector field, namely curl F dot NDS. Okay, so that's the statement. And just to clarify a little bit, so again, you know, we've seen various kinds of integrals. So line integrals, we know how to evaluate. They take place in a curve. You express everything in terms of one variable, and after substituting, you end up with a usual one variable integral that you know how to evaluate. And surface integrals, we know also how to evaluate. Namely, we've seen various formulas for NDS. Once you have such a formula, you do the dot product with this vector field, which is not the same as that one, but it's a new vector field that you can build out of F. You do the dot product, you express everything in terms of your two integration variables, and then you evaluate. So now what does this have to do with various other things? So one thing I want to say has to do with how Stokes helps us understand path independence. So how it actually motivates our criterion for gradient fields. Independence. Okay, so we've said that if we have a vector field defined in a simply connected region and its curl is 0, then it's a gradient field and the line integral is path independent. So let me first define for you what a simply connected region is. So we say that a region in space is simply connected if every closed loop inside this region bounds some surface again inside this region. Okay, so let me just give you some examples, just to clarify. So, for example, let's say that I have a region that's the entire space with the origin removed. Okay, so space with the origin removed. Okay. Do you think it's simply connected? Who thinks it's simply connected? Who thinks it's not simply connected? Let's think a little bit harder. Let's say that I take a loop like this one. Okay, it doesn't go through the origin. Can I find a surface that's bounded by this loop and that does not pass through the origin? Yeah, I can take the sphere, you know, for example, or anything that's just not quite the disk. So, and you know, similarly, if I take any other loop that avoids the origin, I can find actually a surface bounded by it that does not pass through the origin. So actually, that's a kind of a not so obvious theorem to prove, but maybe intuitively, start by finding any surface. Well, if that surface passes through the origin, just wiggle it a little bit, you can make sure it doesn't pass through the origin anymore. You know, just push it a little bit. So So in fact, this is simply connected. That was a trick question. Okay, now on the other hand, a good example of something that is not simply connected is if I take space and I remove the z-axis. That is not simply connected. And see, the reason is, if I look again, say, at the unit circle in the x-axis, sorry, in unit circle in the xy plane, in the xy plane. So if I try to find a surface whose boundary is this disk, well, it has to actually cross the z-axis somewhere. There's no way that I can find a surface whose only boundary is this curve, which doesn't hit the z-axis anywhere. Of course, you could try to, use the same trick as there. Say, maybe we want to go up, let's start with a cylinder. Well, the problem is you would have to go infinitely far because the z-axis goes infinitely far, and you'll never be able to actually close your surface. So no matter what kind of trick you might want to use, it's actually a theorem in topology that you cannot find a surface bounded by this disk without intersecting the z-axis. Yes? Well, a donut shape certainly would stay away from the z-axis, but it wouldn't be a surface with boundary just this guy. Right? It would have to have either some other boundary. If your surface, so maybe what you have in mind is some sort of donut shape like this that curves on itself and maybe comes back. Well, if you don't quite close it all the way around, so I can try to indeed draw some sort of donut here. Well, if I don't quite close it, then it will have another edge at the other end wherever I started. If I close it completely, then this curve is no longer its boundary because my surface lives on both sides of this curve. See, I want a surface that stops on this curve and doesn't go beyond it. And nowhere else does it have that kind of behavior. Everywhere else, it keeps going on. So actually, maybe actually another way to convince yourself is to find a counterexample to the statement I'm going to make about vector fields with curl 0 in simply connected regions always being conservative. So what you can do is you can take the example that we had in one of our older problem sets that was a vector field in the plane, but just, you can also use it to define a vector field in space just with no z component. That vector field is actually defined everywhere except on the z-axis, and it violates the usual theorem that we would expect. So that's one way to check, just for sure, that this thing is not simply connected. So what's the statement I want to make? So recall, we've seen if f is a gradient field, then its curl is 0. That's just the fact that the mixed second partial derivatives are equal. So now the converse is the following theorem. It says if the curl of f equals 0 in, and f is defined it's not the logical way in which to say it. So if f is defined in a simply connected region and curl f is 0, then f is a gradient field and the line integral for f is path independent, f is conservative, and so on, all the usual consequences. Remember, these are all equivalent to each other, For example, because you can use path independence to define the potential by doing the line integral of f. Okay, so where do we use the assumption of being defined in a simply connected region? Well, the way in which we will prove this is to use Stokes' theorem. Okay, so the proof, so I'm just going to prove that the line integral is path independent. The others work the same way. Okay, so let's assume that we have a vector field whose curl is 0, and let's say that we have two curves, C1 and C2, that go from some point P0 to some point P1, the same point to the same point. Well, we'd like to understand the line integral along C1, say, minus the line integral along C2 to show that this is 0. Okay, that's what we are trying to prove. So how will we compute that? Well, the line integral along C1 minus C2, well, let's just form a closed curve that is C1 minus C2. Okay, so let's call C, whoops, so that's equal to the integral along C of f dot dr, where C is C1 followed by C2 backwards. Now, C is a closed curve. So I can use Stokes' theorem. Well, to be able to use Stokes' theorem, I need actually to find a surface to apply it to. And that's where the assumption of simply connected is useful. I know in advance that any closed curve, so C in particular, has to bound some surface. Okay, so we can find S, a surface S, that bounds C because the region is simply connected. So now that tells us we can actually apply Stokes' theorem. Except it won't fit here, so instead I will do that on the next line. That's equal by Stokes to the double integral over S of curl F dot vector ds, or nds. But now the curl is 0, so if I integrate 0, I will get 0. Okay, so I've proved that my two line integrals along C1 and C2 were equal, but for that I needed to be able to find a surface to which to apply Stokes' theorem, and that required my region to be simply connected. If I had a vector field that was defined only outside of the z-axis, and I took two paths that went on one side and the other side of the z-axis, I might have obtained actually different values of a line integral. Okay, so anyway, that's the customary warning about simply connected things. Okay, let me just mention very quickly that there's a lot of interesting topology you can do actually in space. So for example, this concept of being simply connected or not and studying which loops bound surfaces or not can be used to classify shapes of things inside space. So for example, one of the founding achievements of topology in the 19th century was to classify surfaces in space. By trying to look at loops on them. So what I mean by that is if I take the surface of a sphere, well, I claim the surface of a sphere is simply connected. Why is that? Well, let's take my favorite closed curve on the surface of the sphere. I can always find a portion of the sphere that's bounded by it. Okay. So that's the definition of the surface of a sphere being simply connected. On the other hand, if I take what's called a torus, or if you prefer, the surface of a donut, if that's more, it's a less technical term, but it's then that's not simply connected. And in fact, for example, if you look at this loop here that goes around it, well, of course, it bounds a surface in space, but that surface cannot be made to be just a piece of the donut. You have to go through the hole. You have to leave the surface of a torus. In fact, there's another one. See, this one also does not bound anything that's completely contained in the torus. And of course, it bounds this disk that's inside of the torus, but that's not a part of the surface itself. So in fact, topologists would say there's two independent loops that don't bound surfaces, that don't bound anything. And so this number 2 is somehow an invariant that you can associate to this kind of shape. And then if you consider more complicated surfaces with more holes in them, you can try somehow to count independent loops on them. And that's the beginning of the classification of surfaces. Anyway, that's not really an 1802 topic, but I thought I would mention it because it's kind of a cool idea. Okay. Let me say a bit more in the way of, fun remarks like that. So, food for thought. Let's say that I want to apply Stokes' theorem to simplify a line integral along this curve here. Okay, so this curve, it's maybe not easy to see on the picture. It kind of goes twice around the z-axis, but it spirals up and then down. Okay, so one way to find a surface that's bounded by this curve is to take what's called the Möbius strip. Okay, so the Möbius strip, it's a one-sided strip where when you go around, you flip one side becomes the other. So you just, if you want, take a band of paper and glue the two sides with a twist. So that's a one-sided surface. And that gives us actually serious trouble if we try to orient it to apply Stokes' theorem. So see, for example, if I take this Möbius strip and I try to find an orientation. So here it looks like that. Well, let's say that I've oriented my curve going in this direction. So I go around, 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 still go in this direction. Well, the orientation I should have for Stokes' theorem is that when so curve continues here in case. Well, if you look at the convention around here, it tells us that the normal vector should be going this way. Okay? But if we look at it near here, if we walk along this way, the surface is to our right, so we should actually be flipping things upside down. The normal vector should be going down. And in fact, if you try to follow your normal vector that's pointing up, it's pointing up, 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 it will have to go a bit into things, into, down. There's no way to choose consistently a normal vector for the Möbius strip. So that's what we call a non-orientable surface. And that just means, it has only one side. And if it has only one side, then we cannot speak of flux through it because we have no way of saying that we'll be counting things positively one way, negatively the other way, because there's only one, there's no notion of sides. So you can't define a side towards which things will be going positively. So that's actually a situation where flux cannot be defined. Okay, so as much as Möbius strips and Klein bottles are exciting and really cool, well, we can't use them in this class because we can't define flux through them. So if we really wanted to apply Stokes' theorem, because I've been telling you that space is simply connected and I will always be able to apply Stokes' theorem to any curve, what would I do? Well, I claim this curve actually bounds another surface that is orientable. Yeah, that looks counterintuitive. Well, let's see it. I claim you can take a hemisphere and you can take a small thing and twist it around. So in case you don't believe me, let me do it again with the transparency. Here's my loop. And see, well, the scale is not exactly the same, so it doesn't quite match. And it's getting a bit dark. But that spherical thing with a little slit twisting into it will actually have boundary my loop. And that one is orientable. I mean, I leave it up to you to stare at the picture long enough to convince yourselves that there's a well-defined up and down. Okay. So now, in case you're getting really, really worried, there won't be any Möbius strips on the exam on Tuesday, okay? It's just to, show you some cool stuff. Okay, questions? No? Okay, one last thing I want to show you before we start reviewing. So one question you might have about Stokes' theorem is how come we can choose whatever surface we want? Sure, it seems to work, but why? So I'm going to say a couple of words about surface independence in Stokes' theorem. So let's say that I have a curve C in space, and let's say that I want to apply Stokes' theorem. So then I can choose my favorite surface bounded by C. So in a situation like this, for example, I might want to make my first choice be this guy S1, like maybe some sort of upper half sphere. And if you pay attention to the orientation conventions, you'll see that you need to take it with normal vector pointing up. Maybe, actually, I would rather make a different choice, and actually I will choose another surface S2 that maybe looks like that. And if I look carefully at the orientation convention, Stokes' theorem tells me that I have to take the normal vector pointing up again, so that's actually into things. So Stokes says that the line integral along C of my favorite vector field can be computed either as a flux integral for the curl through S1, or as the same integral but through S2 instead of S1. So that seems to suggest that curl F has some sort of surface independence property. It doesn't really matter which surface I take as long as the boundary is this given curve C. Why is that? That's a strange property to have. Where does it come from? Well, let's think about it for a second. So why are these the same? Of course, they have to be the same, so that because that's what Stokes tells us. But why is that okay? Well, let's think about comparing the flux integral through S1 and the flux integral through S2. So if we want to compare them, we should probably subtract them from each other. Okay, so let's do the flux integral through S1 minus the flux integral through S2 of the same thing. Well, let's give a name. Let's call S the surface S1 minus S2. So what is S? S is S1 with its given orientation together with S2 with a reversed orientation. So S is actually this whole closed surface here. And the normal vector to S seems to be pointing outwards everywhere. Okay, so now if we have a closed surface with the normal vector pointing outwards and we want to find a flux integral through it, well, we can replace that with a triple integral. So that's the divergence theorem. that by the divergence theorem, using the fact that S is a closed surface, that's equal to the triple integral over the region inside, let me call that region D, of divergence of curl F dV. Okay. And what I'm going to claim now is that we can actually check that if you take the divergence of the curl of a vector field, you always get 0. Okay? And so that will tell you that this integral will always be 0, and that's why the flux through S1 and the flux through S2 were the same a priori, and we didn't have to worry about which one we chose when we did Stokes' theorem. Okay, so let's just check quickly that divergence of a curl is 0. In case you're wondering why I'm doing all this, well, first, I think it's kind of interesting, and second, it reminds you of the statement of all these theorems and all these definitions. So in a way, we're already reviewing. Okay? So let's see. If my vector field has components P, Q, and R, remember that the curl was defined by this cross product between del and our given vector field. So that's Ry minus Qz followed by Pz minus Rx and Qx minus Py. So now we want to take the divergence of this. Well, so we have to take the first component, Ry minus Qz, and take its partial with respect to x. Then take the y component, Pz minus Rx, partial with respect to y, plus Qx minus Py, partial with respect to z. And, well, now we should expand this, but I claim it will always simplify to 0. Okay, so I think we have over there becomes R sub yx minus Q sub zx plus P sub zy minus R sub xy plus Q sub xz minus P sub yz. Well, let's see. We have P sub zy minus P sub yz. These two cancel out. We have R sub yx minus R sub xy. These cancel out. Q sub zx and Q sub xz. These two also cancel out. So indeed, the divergence of a curl is always 0. Okay, so the claim is divergence of curl is always 0. Del dot del cross F is always 0. And just a small remark, if we had actually real vectors, rather than this strange del guy, indeed we know that if we have two vectors, u and v, and we do u dot u cross v, what is that? Well, one way to say it is it's the determinant of u, and v, which is the volume of a box, but it's completely flat because u, and v are all in the plane defined by u and v. The other way to say it is that u cross v is perpendicular to u and v. Well, if it's perpendicular to u, then its dot product with u will be 0. So no matter how you say it, this is always 0. So in a way, this reinforces our intuition that del, even though it's not at all an actual vector, sometimes it can be manipulated in the same way. Okay, I think that's it for new topics for today. And so now I should maybe try to recap quickly what we've learned in these past 3 weeks so that you know. So the exam is probably going to be similar in difficulty to the practice exams. That's my goal. I don't know if I will have reached that goal or not. We'll only know that after you've taken the test. But the idea is it's meant to be more or less the same level of difficulty. So at this point, we've learned about 3 kinds of beasts in space. Okay, so I'm going to divide my blackboard into 3 pieces. And here I will write triple integrals. We've learned about double integrals, and we've learned about line integrals. Okay? So triple integrals over a region in space, we integrate a scalar quantity dV. How do we do that? Well, we can do that in rectangular coordinates, where dV becomes maybe something like dz dx dy, or any permutation of these. We've seen how to do it also in cylindrical coordinates, where dV is maybe dz times r dr d theta, or more commonly r dr d theta dz. But what I want to emphasize in this way is that both of these you set up pretty much in the same way. So remember, the main trick here is to find the bounds of integration. So when you do it, say, with dz first, that means for fixed xy, so for a fixed point in the xy plane, you have to look at the bounds for z. So that means you have to figure out what's the bottom surface of your solid and what's the top surface of your solid. And you have to find the value of z at the bottom, the value of z at the top, as functions of x and y. And then you will put that as bounds for z. And once you've done that, you're left with a question of finding bounds for x and y. Well, for that, you just rotate the picture, look at your solid from above, so look at its projection to the xy plane, and you set up a double integral either in rectangular xy coordinates or in polar coordinates for x and y. Of course, you can also do it in different orders, and I'll let you figure out again how that goes. But if you do dz first, then the inner bounds are given by bottom and top, and the outer ones are given by looking at the shadow of the region. Now, there's also spherical coordinates. And there we've seen that dv is rho squared sine phi d rho d phi d theta. So now, of course, if this orgy of Greek letters is confusing you at this point, then you probably need to first review spherical coordinates for themselves. Remember that rho is the distance from the origin. Phi is the angle down from the z-axis. So it's 0 on the positive z-axis, pi over 2 in the xy plane, and increases all the way to pi on the negative z-axis. And theta is the angle around the z-axis. So now when we set up bounds here, it will look a lot like what you've done in polar coordinates in the plane, because when you look at the inner bound, the bound on rho, for a fixed phi and theta, that means you're shooting a straight ray from the origin in some direction in space. So you're sending maybe a laser beam, and you want to know what part of your beam is going to be in your given solid. You want to solve for the value of rho when you enter the solid and when you leave it. I mean, very often, if the origin is in your solid, then rho will start at 0. Then you want to know when you exit. And I mean, there's a fairly small list of kinds of surfaces that we've seen how to set up in spherical coordinates. So, if you're really obsessed by this, go over the problems in the notes. That will give you a good idea of what kinds of things we've seen in spherical coordinates. Okay, and then evaluation is the usual way. Questions about this? Okay, so I should say, I'm going to do something bad, but so we've seen, of course, applications of this. So we should know how to use a triple integral to evaluate things like a mass of a solid, the average value of a function, the moment of inertia about one of the coordinate axes, or the gravitational attraction on a mass at the origin. Okay, so these are just formulas to remember for examples of triple integrals. Doesn't change conceptually. You always set them up and evaluate them the same way. It just tells you what to put there for the integrand. Now, double integrals. So when we have a surface in space, well, what we will integrate on it, at least what we've seen how to integrate, is a vector field dotted with the unit normal vector times the area element. Okay, and this is sometimes called vector ds. Now, how do we evaluate that? Well, we've seen formulas for NDS in various settings. And once you have a formula for NDS that will relate NDS to maybe dx dy or something else, and then you will express, so for example, NDS equals something dx dy, and then it becomes a double integral of something dx dy. Now, in the integrand, you want to express everything in terms of x and y. So if you had a z, maybe you have a formula for z in terms of x and y. And when you set up the bounds, well, you try to figure out what are the bounds for x and y. That would be just looking at it from above. Of course, if you're using other variables, figure out the bounds for those variables. Then when you've done that, it becomes just a double integral in the usual sense. Okay, so maybe I should be a bit more explicit about formulas, because there have been a lot. So let me tell you about a few of them. Let me actually do that over here, because I don't want to make this too crowded. Okay, so what kinds of formulas for NDS have we seen? Well, we've seen a formula, for example, for a horizontal plane, or for something that's parallel to the YZ plane or the XZ plane. Well, let's do just the YZ plane for a quick reminder. So if I have a surface that's contained inside the YZ plane, then obviously I will express ds in terms of, well, I will use y and z as my variables. So I will say that ds is dy dz, or dz dy, whatever is most convenient. Maybe we'll even switch to polar coordinates after that, if the problem wants us to. And what about the normal vector? Well, the normal vector is either coming straight at us, or it's maybe going back away from us, depending on which orientation we've chosen. So this gives us NDS. We dot our favorite vector field with it, we integrate, and we get the answer. Okay, we've seen about spheres and cylinders centered at the origin, or centered on the z-axis. So the normal vector sticks straight out or straight in, depending on which direction you do it in. So for a sphere, the normal vector is x, y, z divided by the radius of the sphere. For a cylinder, it's x, y, 0 divided by the radius of the cylinder. And the surface element on a sphere, so see, it's very closely related to the volume element of spherical coordinates, except you don't have a rho anymore. You just plug in rho equals a. So you get a squared sine phi d theta. And for a cylinder, it would be a dz d theta. So, by the way, I mean, just a quick sanity check. You know, when you're doing an integral, if it's a surface integral, there should be two integral signs, and there should be two integration variables, and there should be two d somethings. If you have a wrong number of, you know, if you end up with a dx, dy, dz in a surface integral, something is seriously wrong. Okay, now besides these specific formulas, we've seen two general formulas that are also useful. So one is, if we know how to express z in terms of x and y, and just to change the notation to show you that it's not, you know, set in stone, let's say that z is known as a function z of x and y. So how do I get nds in that case? Well, we've seen a formula that says negative partial z partial x, negative partial z partial y, 1 dx dy. So this formula relates the the surface element on our surface to the area element in the xy plane. It lets us convert between ds and dx dy. Okay, so we just plug in this and we dot with f, and then we substitute everything in terms of x and y, and we evaluate the integral over x and y. If we don't really want to find a way to find z as a function of x and y, but we have a normal vector given to us, then we have another formula which says that nds is, sorry, I should have said it's always up to sign, because we have the two orientation conventions. We have to decide based on what we're trying to do whether we are doing the correct convention or the wrong one. So the other formula is n over n dot k dx dy. Sorry, are they all the same? There's no, well, if you want, you can put an absolute value here, but it doesn't matter because it's up to sign anyway. So, I mean, this formula is valid as it is. Okay, and they will all eventually, I mean, if you try, you know, if you're in a situation where you can apply more than one formula, they will all give you the same answer in the end, because it's the same flux integral. Okay. So anyway, so we have various ways of computing surface integrals, and probably one of the best possible things you can do to prepare for the test is actually to look again at some practice problems from the notes that do flux integrals over various kinds of surfaces, because that's probably one of the hardest topics in this unit of the class. Okay. Anyway, let's move on to line integrals. Now, those are actually a piece of cake in comparison, okay? Because all that this is just integral of p dx plus q dy plus r dz, and then all you have to do is parameterize the curve C to express everything in terms of a single variable. And then you end up with a usual single integral, and you can just compute it. So that one works pretty much as it did in the plane. So if you haven't forgotten what we did in the plane, it's really the same thing. Okay, so now we have three different kinds of integrals, and really well, they certainly have in common that they integrate things somehow. But apart from that, they're extremely different in what they do. I mean, this one involves a function, a scalar quantity. These involve vector quantities. They don't involve the same kind of shapes over which to integrate. Here you integrate over a three-dimensional region. Here you integrate only over a two-dimensional surface, and here only a one-dimensional curve. So try not to confuse them. That's basically the most important advice. Don't get mistaken. Each of them has a different way of getting evaluated. Eventually, they will all give you numbers, but through different processes. So now, well, I said these guys are completely different. Well, but we still have some bridges between them. Okay, so we have two, maybe I should say three, well, two bridges between these guys. Okay, so we have somehow a connection between these, which is the divergence theorem. And we have a connection between that, which is Stokes' theorem. So just to write them again, so the divergence theorem says if I have a region in space and I call its boundary S, so that's going to be a closed surface, and I orient S with a normal vector pointing outwards, then whenever I have a surface integral over S, I can replace it by a triple integral over the region inside. Okay, so this guy is a vector field, and this guy is a function that somehow relates to the vector field. I mean, you should even know how. You should know the definition of divergence, of course. But what I want to point out is if you have to compute the two sides separately, well, this is just, your standard flux integral. This is just your standard triple integral of a region in space. Once you have computed what this guy is, it's really just the triple integral of a function. So the way in which you compute it doesn't see that it came from a divergence. It's just the same way that you would compute any other triple integral. The way we compute it doesn't depend on what actually we're integrating. Stokes' theorem says if I have a curve that's the boundary of a surface S, and I orient the two in compatible manners, then I can replace a line integral on C by a surface integral on S. Okay, and that surface integral, well, it's not for the same vector field. This relates a line integral for one field to a surface integral from another field. That other field is given from the first one just by taking its curl. So after you take the curl, you obtain a different vector field. And the way in which you will compute this surface integral is just as with any surface integral. You just find a formula for NDS, dot product, substitute, evaluate. The calculation of this thing, once you've computed curl, does not remember that it was a curl. It's the same as with any other flux integral. Okay? And finally, the last bridge. So this was like between 2 and 3. This was between 1 and 2. Let me just say there's a bridge between 0 and 1, which is that if you have a function and its gradient, well, the fundamental theorem of calculus says that the line integral for the vector field given by the gradient of a function is actually equal to the change in value of a function. That if you have a curve bounded by P0 and P1. So in a way, actually, each of these three theorems relates a quantity with a certain number of integral signs to a quantity with one more integral sign. And that's actually somehow a fundamental similarity between them. But maybe it's easier to think of them as completely different stories. So now with this one, we additionally have to remember another topic is given a vector field F with curl equal to 0, find the potential. And we've seen two methods for that, and I'm sure you remember them. So if not, then try to remember them for Tuesday. Okay, so Anyway, again, conceptually, we have really three different kinds of integrals. We evaluate them in completely different ways, and first we have a handful of theorems connecting them to each other. But that doesn't have any impact on how we actually compute things.